Hello everyone, welcome to lecture number 54 of the NPTEL course on Riemannian geometry. So last time we stated and proved the Cartan-Hadamard theorem. So that says the following: so let Mg be a complete Riemannian manifold with non-positive sectional curvature. Then for any p, the exponential map turns out to be a covering map, right? And as a consequence of this, if additionally M is simply connected, then we get this very strong result that M is actually diffeomorphic to Rn. Why? Because if M is simply connected, it is its own universal cover, and then Cartan-Hadamard says that the universal cover is actually the tangent space, which is diffeomorphic to Rn. Okay. Alright, so the proof relied on two key ingredients. One was this covering map theorem due to Ambrose, and the second one was the no conjugate point theorem, right. So we did prove the no conjugate point proposition, but I deferred the proof of the Ambrose theorem. So that is what we will do in this lecture, thereby completing the proof of Cartan-Hadamard. Okay, so let me remind you of what the Ambrose result was. So I think I had labeled this as proposition 1 in the previous lecture. Okay, so this says the following: so let Mg and M tilde G be Riemannian manifolds such that M tilde G tilde is complete. Okay. Additionally, suppose phi is a local isometry. Okay, so of course that just means that it is a local diffeo, and G tilde is the same as the pullback of the Riemannian metric via F. Okay. Then the conclusion is that firstly Mg will also be complete, and secondly phi is a covering map. Okay. So this was the proposition which we want to prove in this lecture. So the key point is the following lemma. So let M tilde G tilde and Mg be as above. So that means M tilde G tilde we are assuming to be complete, and suppose I have a surjective local diffeomorphism. Sorry, a surjective local isometry. Then phi is a covering map. Okay, so this basically reduces the proof of so let me make a remark. This reduces proof of proposition 1, at least the second part, to proving that phi is surjective. Okay. So that is what this lemma does. Okay, so let's prove the lemma quickly. Okay. So the idea, recall phi being a covering map, because it is a local diffeomorphism already, is equivalent to showing that phi satisfies the path lifting property. Okay. So that is what I am going to do. I am going to show that phi actually satisfies the path lifting property. So to that end, let gamma be a path and remember, for smooth covering spaces it is actually enough to show the smooth that smooth paths can be lifted, such that let us say the initial point is some p naught, right. Now because phi is surjective implies there exists a p naught tilde in M tilde such that phi of p naught tilde is equal to p naught. Okay. So my claim is that there exists a gamma tilde such that gamma tilde of 0 is p naught tilde and gamma tilde is a lift, which means that gamma is equal to phi composed with gamma tilde. Okay. So how do you prove this? Alright, so let S be the set of all times from 0 to 1 such that there exists a smooth lift of gamma to the interval 0 to t. Okay. So I want to lift it all across the interval 0 to 1, but let us say I have this set S so that you at least have a lift up to time t. Okay. Then note that clearly 0 belongs to S, right, because so in particular this implies that S is non-empty, right, because you just take the constant path, I mean gamma tilde of 0 is p naught tilde, that is a lift for time t equal to 0. So clearly 0 belongs to S. Okay. Also since phi is a local diffeomorphism, you can always locally lift paths because it is a local diffeomorphism. So this implies that S is also open. So as soon as you have a lift up to t naught, you can go a little point beyond that because phi will be a local diffeomorphism near gamma of t naught. Okay. So so clearly S is open. So my claim now is that so let me call this claim 2, let me call that the previous one claim 1, is that S is closed. Assuming this, we are done. Because 0 1 is connected, so since 0 1 is connected, this implies that S will have to be all of 0 1, okay, and then we are done. Why? Because the only non-empty closed and open subsets of a connected space is the full space itself. Okay. Alright, so it all really boils down to proving claim 2. So let us prove claim 2. Okay, so let T be the supremum of S, okay, and let Tk be a sequence increasing to T. So, it is enough to show that T actually belongs to S, right. That will imply that S is closed. Okay. So, for each Tk, since each Tk belongs to S, there exists a gamma k from 0 Tk to M such that, sorry, to M tilde such that gamma k tilde of 0 is P naught tilde, and phi composed with gamma k tilde is equal to gamma on the interval 0 to Tk. So, that means there is a lift up to the time Tk. Okay. So, now my sub claim is that the sequence gamma k tilde of Tk is bounded. Okay. Let us assume this and then complete the proof of the claim. So, assuming this, then by the Bolzano-Weierstrass property, because M tilde G tilde is complete. So, by the Bolzano-Weierstrass property, after passing to a subsequence, gamma tilde Tk converges to some q tilde. Okay. But then if you compose it with phi, if you take gamma Tk, which is phi composed with this, this is going to converge to phi of q tilde, which I will denote by q. Okay. Also, because gamma is a continuous curve, this is going to tend to gamma of t. So, we basically get that gamma of capital T is this q. Okay. So, now we use the local diffeomorphism property. So, let V tilde be neighborhood of q and q tilde such that phi from V to V tilde is a diffeo. Okay. But then you can always lift the curve beyond. So, the point is that this is your q. For some large enough k, you have these points gamma of Tk that lie in this neighborhood V, which is diffeomorphic to this neighborhood V tilde around q tilde, right, and you have these so you have this gamma here, and upstairs you have this gamma k all the way up to gamma k of Tk. Okay. But now clearly one can always use this local diffeomorphism to construct a lift beyond the point T. Okay. So, the point is that you already have a lift of the curve up to this point. For this bit, you can just use the local diffeomorphism to obtain a lift. Okay, one can use the local diffeomorphism to obtain a lift of gamma up to the time t equals capital T. So, that just implies that capital T also belongs to S, and we are done, right. So, it all boils down to proving this sub claim. So, let us quickly prove that. Okay. So we have to show that it's bounded. So let's try to estimate the following distance. So let's take the distance from P naught tilde to gamma k tilde of Tk. Now note what is happening is you have your P naught tilde here, you have a lift of gamma up to this point gamma tilde of Tk, right. So that means that the distance between this point and this point will at least be as much as the length of gamma k tilde, right. So by definition of the distance function, this is less than equal to the length of this curve. Okay. But now phi is a local isometry, so this is equal to the integral from Tk of d phi applied to gamma k tilde. Okay. But by the chain rule, d phi applied to this velocity vector is simply the velocity vector of gamma, because gamma k is the lift, right. So because gamma is equal to phi composed with gamma k tilde, this implies that this is the same as this. Okay. But then that is of course less than the length of gamma, which is a finite number. Okay. So clearly this forms a bounded sequence, and that proves the subclaim and hence the lemma. Okay. Alright, so now I am going to use this lemma to prove the proposition of Ambrose. Before I prove the proposition of Ambrose, so some general remarks which will be used. So firstly, we know that phi is a local isometry. So what this shows is that if gamma is equal to, so this is something we already used in the argument of the proof, then this implies that the two speeds are the same. Right. And the second point is that phi takes geodesics to geodesics. Okay. So this is due to the naturality of the connection. Okay. However, a sort of caveat is that minimal geodesics may not be taken to minimal geodesics. Okay. All right. So so for instance, I mean we see that in the case of a cylinder, for instance, that's locally isometric to Rn, but straight lines are taken to helices. Helices are not always minimizing. I mean you might have a helix. Right. So in any case, so minimal geodesics may not be taken to minimal geodesics. Okay, so let us prove the proposition. So remember, all we have to do is to prove surjectivity of the map, right, because then by the lemma phi will be a covering map. So this has several steps. So the first step, or maybe let me write it as claims. So the first claim is a claim about geodesic lifting. Okay. So this says the following. So let gamma be a geodesic and P naught be the value of gamma at some T naught. Suppose P naught lies in the image of phi. So remember, we still do not know whether phi is surjective, that is something we have to show. So suppose P naught lies in the image of phi. So let us say P naught is phi of P naught tilde, then there exists a unique geodesic gamma tilde from I to M such that gamma tilde of T naught is P naught tilde and it is a lift. Okay. So what is the proof of this? Okay, so let V naught be the velocity vector of gamma at T naught, okay, and V naught tilde is its inverse image under the derivative map. So this is the derivative at P naught tilde inverse of V naught. We know that phi is a local diffeomorphism, so the derivative in particular is an isomorphism at the level of tangent spaces. So the inverse map exists, right. So let V naught tilde be the inverse of the derivative map at P naught tilde of V naught. So simply take gamma tilde of T to be the exponential at P naught tilde of T minus T naught times V naught tilde. Okay, so clearly if you plug in T naught, this is going to be the exponential evaluated at the 0 vector, which is of course P naught tilde. Also the initial velocity vector is clearly going to be V naught tilde. So now I want to claim that this gamma tilde actually does the work. So in other words, it's actually a lift of gamma. So let's push this curve forward. Okay, so let's take phi composed with gamma tilde. Okay. So then notice that that sigma is a geodesic by the remark that I made just before starting this proof, since phi is a local isometry. Also, what is sigma at T naught? Well, that is just phi at gamma tilde of T naught, which is just P naught. Okay. Also, what is the derivative of sigma at T naught by the chain rule? That is basically this at P naught tilde acting on the derivative of gamma tilde at T naught, but that is just V naught tilde. But by our choice of V naught tilde, this is simply V naught. Okay. So that means sigma is another geodesic with the initial conditions that sigma at T naught is P naught, sigma prime at T naught is V naught. So by the uniqueness of geodesics, sigma and gamma have to be identical, which means that gamma tilde is a lift of gamma, and we are done. Okay. So that completes the proof of the first claim. Okay, my next claim is that M is actually complete, Mg is complete. Okay. So let us just take some p in the image of phi. So, let P belong to the image of phi, and let us say P is given by phi of P tilde. Okay, let us take a tangent vector at that point, and as in the first step above, take the inverse image of it under the derivative map. Okay, so and let gamma tilde of t be equal to exponential of P tilde of t times V tilde. Okay. Then mg complete, sorry, m tilde g tilde complete implies gamma tilde exists for all time. Okay. But now you can just push that forward. So, let gamma of t be equal to phi composed with gamma tilde of t. Then as again exactly as in the first step, gamma is a geodesic for all time t, gamma of 0 is p, and by the chain rule gamma prime of 0 is v. So, v was an arbitrary tangent vector, and we have shown that there exists a geodesic with that as the initial velocity vector. Okay, so this whole thing implies that at this point p, the domain of the exponential map is all of the tangent space. And then by the Hopf-Reno theorem, it is to check geodesic completeness, it is actually enough to check that the domain of the exponential map at a single point is actually the entire tangent space. So, then by the Hopf-Reno theorem, this implies that Mg is complete. Okay. All right, and finally we come to the third claim, that phi is surjective. Then by the lemma, this would complete the proof of the proposition. Okay, so why is phi surjective? Well, right. So let P as in the second step be in the image of phi. Say P is given by phi of P tilde, and let Q be another point in M. I want to show that Q also belongs to the image under phi. Okay. So now because Mg is complete by Hopf-Reno, this is again by Hopf-Reno, there exists a tangent vector. So basically you can connect P and Q by a minimal geodesic. So there exists a tangent vector V in at P such that Q can be written as this. Okay. So we just now consider the following geodesic: gamma of t is the exponential of TV. Okay. So so by the first claim, this is a geodesic on M. By the first claim, there is a lift to a geodesic upstairs. So claim 1 implies there exists a geodesic gamma tilde from 0 to 1 to M such that gamma tilde of 0 is this P tilde, and gamma is the push forward of gamma tilde. But notice, what does that mean? That just means that if you plug in gamma of 1, so if you plug in t equals 1, then of course by our choice of gamma this is equal to q, but then that will equal phi of gamma tilde of 1. Okay. Or in other words, that implies that q lies in the image of phi under M, sorry, of image of M under phi, right. So since q was arbitrary, this implies that phi is surjective, and we are done. Okay, so this completes the proof of the proposition. Okay, so in the next few lectures I am going to study complete manifolds. So Karta-Hadamard was about complete manifolds with an upper bound on the sectional curvature. In the next few lectures I am going to study complete manifolds whose sectional curvature is constant, and then we will prove something which we will call the uniformization theorem. So we will prove a theorem that completely characterizes all Riemannian manifolds whose sectional curvature is a constant. Okay. Alright, so that is it for the next few lectures. Thanks for your attention, and I will see you next time around. Thank you.